prove that that is the solution to that equation over here. Okay, it's a proof that you see in signal processing a lot, but this is non-causal. But in signal processing, it would be causal. Okay, so Y looks like this, right? So it's non-analytic at the origin. So a cartoon picture of this function will look something like this. On the right-hand side, it might be oscillatory. On the left-hand side, it might be oscillatory. But then the slope is not continuous then. Okay, this is a cartoon picture. Because that is a complex function, you cannot draw a complex function. I just give you a cartoon picture of how that function looks like. So if you were to differentiate this with respect to y1s, on the right-hand side, you will have iky, e to the iky, y, when y is larger than 0. And then on the left-hand side, you have to remove this magnitude sign. Replace y with a minus y. And when you differentiate it, you will get this as a solution. So you can see that the slope is not continuous. There's a jump in the slope. How big is the jump? The jump is iky on one side, and then it's minus iky on the other side, right? When y is equal to 0. This is y is equal to 0. There's a jump discontinuity. This jump is 2ky. Again, it's a cartoon picture because it cannot draw imaginary numbers. Okay? So if I differentiate this jump discontinuity one more time, what do I get? If I differentiate this one more time, I get a delta function out of this jump discontinuity, and the jump discontinuity gives me a delta function of this amplitude plus the higher order term. The next order term, but those order terms should cancel to 0. Okay, should cancel to 0, and hence the function should be picked so that the jump discontinuity is exactly equal. It seems that I need a minus sign somewhere. It seems that this might be a minus sign in order for jump discontinuity to match up. Well, no minus sign because there's a minus sign here. Okay, so no minus sign. So that is the correct solution. Okay, everybody agrees? Aditya, are you satisfied with the proof?
You are going the other way around.
No, I'm proving it. I'm starting with that and then proving it. But if you want me to go the other way around, it's more laborious. I say, oh, on the right-hand side, this thing is 0. So the right-hand side must have this solution for right-hand side. And then on the left-hand side, that thing is again 0. The wave must be left traveling. This is the left-hand side solution, left of this thing. I don't know what the amplitudes are. A1, A2. Okay. A1 must be equal to A2, you know why? A1 must be equal to A2. I know the boundary condition, right? I already taught you how to eyeball an equation and figure out what the boundary condition should be. If the most I have is the delta function on the right-hand side, the function itself must be continuous. It cannot have a jump discontinuity. So A1 must be equal to A2. So you get rid of one unknown, and then you have to figure out the third unknown by matching the jump. Okay, you match the jump condition very similar to this manner, and then you end up with the correct solution. Okay, so that is the correct solution. So wonderful. We have this correct solution. What we say is that we now have we now have the knowledge of what this should be. That thing is just equal to that. So we have Pxy must be equal to, if I plug in things correctly, I over 4 pi minus infinity to infinity dkx into I ky y, and then putting in the ky here, because there's a ky coming from here, and then I should put a magnitude there, plus I kxx. This is my solution, my full complete solution with everything determined. But I've also found another solution for this equation. I've also found another solution for that equation that I had erased. The other solution was using a different argument, using the Green's function technique. The other solution was that. But by the uniqueness principle, if I solve this problem with the correct boundary condition, the boundary condition being the radiation condition here, in fact. The wave satisfies the radiation condition at infinity. It satisfies the singularity condition at the origin. These two must be the same. So I end up with this integral identity that this cylindrical wave, this Hankel function, must be 1 over pi dkx e to the kxx plus I ky y over ky. Okay? Look at what this equation is saying now to you. This equation is saying something quite different. Okay? What is the right hand side of that equation? What is it stating? If you look at the integrand, it's calling out loud to you as to what this means. What is that representing? Yes? Yes, Chris? What do you think it represents? Somebody say something. I don't remember. I don't know who it's from.
It's a plane wave.
It's a plane wave, right? This is just a plane wave. So y larger than 0, this is a plane wave propagating in one direction above the y less than 0. You have to replace it with the minus sign. This is another plane wave propagating downward. You remember what ky was? Ky was just square root of k rho squared minus kx squared. Okay, so kx squared plus ky squared is equal to k rho squared, which is the plane wave relationship. So what we have successfully done is to write a cylindrical wave. This is a cylindrical wave as an integral summation of plane waves. And above the y is equal to 0 line, the plane waves are propagating upward. So if I were to draw a picture in this line, this integral summation corresponds to all different kind of kx numbers, which means that the plane waves are propagating with different inclined angles. They're all propagating upward above the line. But below the y equal to 0 line, this is y, this is x. Okay, the waves are propagating downward. So can you see the physical picture clearly? What happens if kx is larger than k rho?
You get a bound solution.
What is that?
You get a bound solution.
A bound solution?
Yeah.
What do you mean by bound solution?
For imaginary ky, that's a bounce, like a decaying solution outward towards.
Oh, there's an evanescent wave, right? We don't call it a bound solution, we call it an evanescent wave, right? The wave is bound to the source. It's an evanescent wave. for kx larger than k rho, ky becomes pure imaginary. I cannot draw rays anymore for this plane. Those are actually corresponding to Ebernoulli. So as you integrate on the complex kx plane, real kx. So this k rho point is very important. K rho, and this is minus k rho, as you integrate. Okay? And then for k rho, for kx larger than k rho, this is the kx plane, okay? I often will just denote it like that. For 0 to k rho, the waves are propagating. But for kx larger than k rho, the waves are evanescent. So all waves are important in this expansion. Evanescent waves as well as propagating waves. But what happens when kx equals k rho? Kx equals k rho, ky goes to 0. This thing becomes singular, right? The integrand becomes singular. How do we define this integral? When kx equals k rho, it becomes problematic, doesn't it? So what do we do in that case? There's something wrong with this integral identity when kx equals k rho. How do we get ourselves out of this bind? Yes? Choose a different integration path, right? And that's what Junwei proposes. But how do we know how to choose a different integration path? We started out with Fourier transform property. Fourier transform property dictates that this integration path is on the real axis. So we go back to square one and see where we went wrong. Why is it that when kx equals k rho, this integral becomes undefined? So we go back to square one and ask ourselves, when can we really write something down like this in terms of a Fourier transform? In other words, when does Fourier transform exist? What is the requirement for the existence of a Fourier transform? Do you remember from your signal processing course? Aditya, do you know? When does the Fourier transform of a function exist? Yes?
It's linear.
Linear doesn't make it like if phi of x is equal to x. Does it make it? Can you write phi of x in terms of kx e to the I kx? Can you find such a function that this is true? No, right? So linearity is not the criterion for the existence of a Fourier transform. Go back to your signal processing
Time
course.
invariant.
What?
Time invariant.
Time invariant. Well, there's one of the properties in linear time invariant system theory, but it's not the criterion for the requirement for the existence of Fourier transform. Yes, Kurt?
Support limited.
What?
Support limited.
Support limited. Very good. That is also something that guarantees the existence of Fourier transform, but not the most general one.
The magnitude is integral or it's squared?
Okay. The function has to be absolutely integrable. This is correct mathematical term. Let me prove it. Let me prove it. Okay. So if you write something like this, when does this integral exist? Okay? When does this integral exist means that the left-hand side is always finite. You can always perform in this integral and arrive at something that's finite on the left-hand side. So one criterion is that this thing has to be less than infinity. That's what we mean when we say that this integral exists. Okay, this integral exists. But we know that from triangular inequality that if you have x1, two complex numbers z1 plus z2, if these are complex numbers, This is true, right? This is true for complex numbers. It's called a triangular inequality. But since complex numbers on the complex plane is like a vector product and vector addition, this is true. So I can apply this to that and say that this must be equal to the magnitude of summation must be summation of magnitude. This is just summation of magnitude. So this thing must be equal to, less than or equal to that. This thing must be less than or equal to that. And then as long as this is less than infinity, if this is less than infinity, then the Fourier transform exists. So when the function is absolutely integrable, okay, when you take the magnitude of the function, the absolute magnitude of the function that is integrable, then the Fourier transform exists. So in order to write something like this, we have to guarantee that this function is absolutely integrable. If it's not, then we actually cannot write things like this. Or in order to write this like this, or in order to derive this from that, we have to guarantee that this function is absolutely integrable. Okay, that this function is absolutely integrable. Otherwise, we cannot have a Fourier transform relationship like that. Okay, so many of these functions are not absolutely integrable. This function, which is what I sketched over here, if I were to look at it, it's actually not absolutely integrable. Because as k rho tends to infinity, this thing goes like 1 over square root of k rho e to the I k x x. Then if you ask yourself, is this absolutely integrable? If I take its absolute magnitude and integrate it, if I take its absolute magnitude, this should be k rho. If I take its absolute magnitude, I have a function like this. Dx, right? Dx. Is this absolutely integrable? And this is x squared plus y squared dx. And this is x goes to infinity. This actually is more than that. This is 1/4. So this is actually 1 over x dx. Okay, when x becomes very large, I cannot integrate this. 1 over square root of x cannot be integrated. 1 over square root of x, when I integrate it, becomes x to the half, right? When I integrate this, I get this, and I cannot evaluate them in endpoints. So they're not absolutely integrable. So when I write something like this in a Fourier relationship like that, I have violated a very fundamental tenet or theorem of Fourier transform. So I cannot do that. And how can I make this derivation kosher or legitimate? I have to introduce some laws. If I introduce some laws, if I make k rho have a real part and an imaginary part, just an infinitesimal small imaginary part. When I take the absolute amplitude of this, the imaginary part will cause it to decay exponentially. So when I do this test, there will be an exponential decay in my integrand, and the function becomes absolutely integral. So all this process will only go through if an infinitesimal loss is introduced. Otherwise, I cannot actually say things like that. Okay? So if I introduce a little bit of loss, k rho becomes something like this. Then the story becomes quite different. If I have k rho will be a complex number now over here, and the complex number over here. Minus k rho will be a complex number over there. And my Fourier transform path, according to Fourier transform theorem, is still on the real axis. And now the Fourier integral is well defined, completely well defined from minus infinity to infinity. Because I have stuck to the correct tenet of Fourier transform theory and arrive at this. Is this clear to everybody? Okay, very good. Okay, so that identity holds true only if I make K rho to correspond to a lossy medium, having a small imaginary part. Otherwise, this identity does not hold true. However, you can be clever about it and say that after I have derived this identity, I can redefine the contour of integration, that instead of integrating right on the ray axis, Cauchy's theorem and complex variable theory allows me to integrate on a path that looks like this. Because I'm going to have a small amount of loss. The two integrals have not changed according to Cauchy's theorem, right? Because integrating on the ray axis and integrating on this newly defined path give me the same integral. But what is the advantage of this newly defined path? I can let the loss be 0 and loss be infinitesimally small, vanishingly small, until it goes to 0 and my integral is still well defined. So I can arrive at an integral identity that is valid, that's legit, that's kosher, even when I don't have loss. Then I have to define a new path of integration. Okay. So that is the story behind it. Are there any questions regarding this derivation? So you cannot deform the path until you understand why it doesn't work. After you've understood why it did not work, introduce some loss, you can deform the path a little bit, and then define that to be your new path using Cauchy's theorem. And then using Cauchy's theorem, you can say that I can have the path here with a new path. Okay, and this identity would still hold true in the limit of no loss. Okay. Okay, let's have more fun with other integral identities then. So this is a very important integral identity that becomes very useful. So, we have this very important integral identity. Ky. Okay, let me set x is equal to rho, y is equal to 0. Okay, I just set my coordinate system so that my observation point is right at here. Okay, this is y, this is x is equal to rho. So this is a cylindrical coordinate system. And then I can fold this integration around and make it into a 2 for the positive and the negative part, and convert this into a cosine integration. Okay, and convert this into a cosine integration, and ky, if you recall, is equal to k rho squared minus kx squared. Okay, let's assume that k rho is almost real. It's slightly complex with the infinitesimal small imaginary part. Okay, so if you were to look at this integral, if I were to integrate from 0 to k rho, the kx, ky would be purely real. If I just take the first part of this integration, it has to be purely real, and then there's a remaining part, which is k rho to infinity dkx, cosine kx pro over ky. Okay, this part is purely imaginary, right? Because ky becomes imaginary in this domain, in this range of integration. This one becomes pure real. But we know of something about Hankel function. Hankel function is actually a sum of Bessel function plus Neumann function, and sometimes this is written as y. Sometimes this is also written as n0. Sometimes Neumann function is written with the y, sometimes it's written with the n. They both refer to the same thing. And with this Bessel function with the real argument is purely real. This Neumann function with the real argument is also purely real. So this part must be this part. This part must be that part. So we end up with a new identity that the Bessel function must be equal to okay, we have a new integral identity now. And then the second part is equal to that part. Can anybody give me a physical reason why that the Neumann function is associated with the evanescent wave? Bessel functions are associated with propagating part of the spectrum. As we say, if we integrate from here to here, these waves are propagating. But if we integrate from here to here, these waves are evanescent. If you look at this identity now, the evanescent waves are associated with the Neumann function, the propagating waves are associated with the Bessel function. Give me the physical reason why.
Because J0 is regular, Y0 is singular.
Why do singular waves have to be associated with the evanescent spectrum? And the regular part does not have to be associated with the evanescent spectrum at all. Well, let's go back to this integral. What does the evanescent part of the spectrum mean to you in Fourier transform theory? Evanescent part of the spectrum means that I'm dealing with high kx wave numbers. What does high kx value mean to you? If you have a Fourier transform integral, if this is actually a Fourier transform, if you have large kx's, what does it mean to you?
High variation in the x direction.
Yes?
The frequency, the change in the x direction is very fast.
You have highly oscillatory integrand, right? What does highly oscillatory integrand mean to you? What would the high frequency component of this Fourier transform map to in the real space? You learn from your signal processing course, right? High frequency means what in the time domain?
It would mean the sharp edges.
The singularity is very good, okay? High frequency part of this spectrum maps to the singular or rapidly varying part of the coordinate space, okay? The coordinate space function now is divided into two functions. This one has a singularity, this does not. If you look at this one, when rho is equal to 0, will go to infinity. This one, when rho is equal to 0, does not go to infinity. This part needs evanescent spectrum. This part does not. There's the physical meaning. Okay, why you need evanescent spectrum to represent the singularity of a function. The singularity means high frequency spectral component. Just like in your signal processing course, any jump discontinuity gives rise to high spectral component. Any singularity in the time domain gives rise to high frequency in the Fourier transform domain. So the same thing Well, see, I just want you to have this insight. So the Bessel function is associated with the propagating spectrum because we don't need high frequency component to expand a regular function. Okay, does that sound fair? Sounds very fair, right? Okay, then let's manipulate this into something even nicer. Let me re-expand and go backward and write this as minus k rho to k rho. Unfold this integral now, since I have folded it, and convince you that after I have folded, it becomes purely real. And this actually gives you a very nice picture, physical picture. Okay, I can make this into an even nicer physical picture by assuming that kx is k rho cosine of alpha. I do this change of variable. Okay, ky is actually k rho squared minus kx squared will be k rho sine of alpha. Okay, and then the kx is the alpha sine alpha k rho, right? Then we take the kx of that equation and get that. There should be a minus sign there. Okay. Then I should do things the other way around. Sorry. I don't want the minus sign here. I want a plus sign there to make things simpler. Sorry. I put a sign there. I put a cosine here. I put a cosine there. Then there's no minus sign. That is the change of variables that I want. And if I substitute that to the above now, k rho happens when sine alpha is pi over 2. Minus k rho happens when alpha is minus pi over 2. So this range of integration after this change of variable becomes just minus pi over 2 to pi over 2. The kx becomes this. Okay. K rho cos alpha is just ky. Okay, k rho cos alpha is just ky. This ky and that ky will cancel. And then I will have kx is equal to k rho sine alpha rho. Okay. So this integration becomes extremely simple. This is all I have. The sine alpha, of course, looks something like this between this range of integration. Okay? But it doesn't matter now. If you look at this sine alpha is going to look like this. And if I can extend my range of integration to minus pi and pi, I just add this little piece there, add this little piece there. This piece and that piece are of the same sign. This piece and that piece are of the same sign. So I can easily expand my range of integration and say that this is in fact equal to 1 over 2 pi, change the 1 over pi to 1 over 2 pi, double my range of integration from minus pi to pi, right? Minus pi to pi, the alpha e to the I k rho sine alpha. Okay, minus pi to pi. So I'm integrating over a full range of 2 pi now. But this is a 2 pi periodic function. I'm integrating over a full range of 2 pi. So it doesn't matter where I start or where I end now. Okay? I can rewrite this and say that this must be the same as this. Because this is a 2 pi periodic function, agree? More interestingly, it doesn't matter whether this is a sine or a cosine. I can replace it with a cosine. But more interestingly, since this is 2 pi periodic, I can replace it with just any 2 pi periodic function, this still holds true, right? So a Bessel function is this. But this now has a nice physical meaning. What is this nice physical meaning that it has? If the vector k rho is written by kx plus yky, if the vector rho is written by x plus yx with kx, ky, and the vector k rho looks something like this, and making an alpha with the real axis. Okay, this vector k rho looks like this. And for the other vector x, y, and this is the vector rho making an angle phi like that. And if I take the dot product of k rho and rho, this is just k rho, rho, the magnitude of k rho, magnitude of rho, times the angle between them. The angle between them is just alpha minus phi, right? Now I can write this very suggestively, saying that Bessel function is nothing but an integral summation over all angles between 0 and 2 pi of a this wave. But what is this wave now? What is this wave? You learned that from your undergraduate course, right? What is that wave? Aditya, what is that wave?
Plane wave.
A plane wave, right? It's just a plane wave propagating in the k rho direction. And it's pointing in the alpha direction. And that plane wave is propagating over all alpha direction, and it changed my alpha from 0 to 2 pi. That's what a Bessel function is. A Bessel function is an integral summation of plane wave propagating in all the